Executive Summary. Wireless power is maturing across several complementary approaches: near-field inductive, Qi, MagSafe; mid-range resonant, Witricity style; RF, over-the-air, PowerCast, ASSIA, Energis; optical, laser beaming; and large infrastructure dynamic inductive systems for EVs. The near-term commercial growth is strongest in consumer device pads, Qi, Qi2, and EV wireless pilots, static pads plus dynamic roadway pilots. Mid and long-range over-the-air power for small sensors is commercially feasible. Higher power long-range systems are still experimental and highly regulated. Key hurdles remain: efficiency at distance, safety, EMF regulation, alignment and interoperability, infrastructure cost for EV road embed, and conversion loss for RF optical links. 1. Technology categories: how they work and where they fit. A. Near-field inductive, magnetic induction. Use: phone pads, toothbrushes, small appliances. Very high efficiency at contact, very short gaps. Latest standard progress. Qi, WPC, remains dominant, and Qi2, 2024-2025 upgrades, brings faster, more interoperable, magnetically aligned charging for phones and wearables. B. Magnetic resonance, mid-range resonant inductive. Use: charging with small spatial tolerance, a few cm to decimeters, EV static pads, some industrial, medical. Companies like Witricity have pushed resonant WPT for EVs and other applications. Research shows new coil phase tricks improving transfer distance and efficiency. C. Dynamic inductive, electric road systems, EV in motion charging. Use: roadway coils embedded under asphalt to charge vehicles while driving, or at stops. Pilots are running on highways and test tracks. Provides high power, tens to hundreds of kW, in pilot systems but requires heavy infrastructure. D. Radio frequency, RF, over-the-air power. Use: low-power remote sensors, IoT, battery-free tags. Companies like PowerCast and ASSIA, CODA, target microwatt-milliwatt delivery to distributed sensors. Energis has continued R&D, commercial efforts. RF power is attractive for many remote sensor use cases but limited by power density, efficiency and regulation. E. Optical, laser beaming. Use: point-to-point high-energy transfer across meters to kilometers. Research, demonstration. Recent experiments include kilometer-scale laser testbeds by industry, academia. Optical links can deliver higher power per beam but require precise pointing, clear line of sight, safety interlocks, and airspace regulations. 2. Notable companies, pilots and prototypes. Who's doing what? Witricity, leader in resonant WPT and EV wireless charging research and partnerships. Vehicle OEM trials, commercialization. Electrian, Vinci, Gustav Eiffel Univ. Real-world dynamic EV roadway pilots, e.g., A10 near Paris. demonstrating multi-vehicle dynamic charging up to hundreds of kW in tests. This is one of the highest profile open highway pilots. PowerCast and ASSIA. RF power for sensors, IoT. PowerCast emphasizes many patents across microwatt right-pointing arrow kilowatt range, mostly in low-power IoT. Energous, publicly reporting ongoing R&D and business development in wireless power. Quarterly reports in 2025 show activity. Their focus historically has been RF, with long-range ambitions. NTT plus Mitsubishi Heavy Industries, and others, optical wireless power experiments, kilometer demo on runway, showing the feasibility of long-distance optical beaming in controlled conditions. Automakers and OEM labs, e.g., Mercedes experimental vehicle ELF testing megawatt charging systems plus wireless inductive methods in lab platforms. R&D platforms integrate multiple charging techs. 3. Standards and regulation. What's enabling interoperability and safety? Qi, Wireless Power Consortium, still the dominant consumer standard. Qi 2, rolled out through 2024-2025, improves magnetic alignment and interoperability for modern phones. SAE J2954 and related IEC 61980 series, the automotive EV wireless charging standard family, defines frequencies, interoperability, alignment, EMF, safety, and has workstreams for static and dynamic EV charging, J2954 halves, J2954 thirds. This standardization is crucial for vehicle OEM adoption. Spectrum and safety regulation. RF and optical beaming require national regulator approvals, FCC, ETSI, etc. And governments are beginning to open industry bans for specific WPT use cases in controlled scenarios. 4. Engineering and business limitations. What's holding things back? Efficiency versus distance. Magnetic induction is efficient at close range. Efficiency rapidly drops with separation. Resonant techniques extend range but still lose energy and require larger coils, structures. RF and optical methods can reach farther but with low power density and conversion inefficiencies. Safety and EMF exposure. High power mid, long range transfer raises bio-EMF, interference and aviation, light exposure concerns. Standards and safety tests are needed for deployment. Cost and infrastructure disruption. Embedding coils in roads or retrofitting buildings is capital intensive. Dynamic roadway charging faces civil engineering, maintenance and coordination challenges. Regulatory and public acceptance. Long-range beaming, RF, laser, requires regulatory paths and public trust, e.g., airspace safety for lasers. 5. Short-term and medium-term product roadmap, realistic timeline. Now -1 year, 2025-2026. Faster phone wireless pads widespread. Qi 2 adoption increases in flagship phones and chargers. More EV wireless pilot deployments and vehicle R&D platforms. OEMs testing static pads plus dynamic road pilots. Expect more public sector pilots in Europe, Korea, and US states. Commercial RF power modules and sensor-targeted solutions expand for industrial IoT, asset tracking, and battery-assisted sensors. 2 to 5 years, 2027-2030. Niche deployments of dynamic EV charging on freight corridors, bus routes, logistics hubs, mainly in government-backed pilots or private fleets where ROI is clear. Improved mid-range resonant products for specialized industrial, medical uses where contactless power and spatial freedom matter. 5+ years. Broader infrastructure adoption is possible but depends on cost declines, standards convergence, and regulatory clarity. Long-range high-power beaming, optical, microwave, could appear in specialized contexts: drones, disaster response, space-to-ground experiments, before consumer ubiquity.